Hi guys, we're going to go ahead and finish up Unit 7 by talking about the solubility of different substances. So we're going to go through section 711 all the way through 713. This last section, 714, is going to be discussed actually in Unit 9. So we'll just do those last three sections today. So let's go ahead and get started. All right, here we go. So we're talking about today something that is called solubility equilibrium. And basically all that is we're talking about equilibrium reactions, so reactions that go in the both forward and reverse directions. But we're talking about those salts that are usually insoluble. So back in Unit 3, I think it was Unit 4 maybe, we were talking about the solubility rules and how to know if salts are soluble or not. Those salts that are not soluble are actually just a tiny bit soluble, and so we're going to be using that information and those values to talk about concentrations of ions that are dissolved and all of that. So KSP is going to be the K value of the equilibrium reaction between a solid salt and its aqueous ions when just that tiny bit of it dissolves. Now, when we write our KSP value, it's the same as writing any other K value for equilibrium. It's going to be products over reactants, but the difference is when we're dealing with KSP versus KC or KP or any of that kind of stuff, remember that we don't include solids in our equilibrium expression. And for KSP, our reactants are always going to be solids, so those reactants are not going to show up in our K expression. We're just going to have our concentration of products to deal with. So generally speaking, the larger the KSP value, the greater the solubility is going to be and the greater concentration of ions present. So we're looking for bigger KSP values means more soluble, smaller KSP values means not very soluble. So KSP expressions, let's just take a look at this one, magnesium phosphate. So remember when we're dealing with ionic compounds that dissolve, so instead of this just going in the forward direction, it can also go in the backwards direction. This is a solid. When it breaks apart into 3 magnesium ions. So when we write our equations, we have to show our coefficient to show how many there are. That comes from this number right here. We have to show the charge as well. Aqueous means that it's dissolved in water. And then for phosphate, there are 2 of those. Let me include that. 2 phosphate ions dissolved in water when magnesium phosphate dissolves. Most of it won't dissolve. A tiny bit of it will. So when we write that KSP expression, it's going to be the concentration of my magnesium ion cubed. My coefficients still become the exponents, and then also times the concentration of phosphate squared. Okay, so let's go ahead and take a look at an example. A super common question with solubility reactions is going to be asking you to solve for what is called the molar solubility. That's going to be in units of molarity, and it's going to be basically the concentration of the salt that actually dissolves versus the concentration of the salt that doesn't dissolve or stays solid. So we're going to be looking at ice tables again for this. We're going to be solving for X. When you solve for X, that's going to equal your molar solubility. In some textbooks, you'll see instead of X in their ice table, they'll use S to represent solubility. But just for keeping it simple, we're going to just use X just the way we did with all of our other ice tables. So if we're calculating the molar solubility for silver sulfide and they give us the KSP value, look at that KSP value, really small, times 10 to the negative 49. That means most silver sulfide will not dissolve, but a tiny, tiny amount will. So first thing we have to do is correctly write our formula. So sulfide is -2, silver is +1. So that formula is going to be Ag2S. I have my double-sided arrow. That will break apart into 2 silver ions and 1 sulfide ion. So since this is solid over here, we don't have to fill in anything from my ice table. Here I'm going to have 0 plus 2x and 0 plus x right here. And I'm going to go ahead and write my KSP expression. So we're going to solve these problems, very similar to how we solved all the other equilibrium problems. We're going to write K expressions. We're just going to label it specifically KSP. We're going to do our ice tables, and then we're going to solve for x. So my KSP expression is going to be my silver concentration squared and my sulfide concentration just to the first power. They give me the KSP value in the problem is 1.6 times 10 to the negative 49. Then I'm going to go ahead and substitute in everything from my equilibrium row here, just like we did before. That's going to be 2x squared times x, which is equal to 4x cubed. So from there, we just need to go ahead and solve for x. You should be able to, with 4x cubed equal to your KSP value, solve for x, which will be equal to 3.42 times 10 to the negative 17. Units for this are in molarity, so this is my molar solubility. That basically means that 3.42 times 10 to the negative 17th moles per liter of silver sulfide will dissolve in water. All right, let's take a look at another example here. We've got magnesium hydroxide. They give us the molar mass here. That's going to be helpful in just a second. We want to calculate the number of grams of magnesium hydroxide that are dissolved in 100 milliliters of solution, and they give us the KSP for magnesium hydroxide. So anytime they give us the KSP for anything, that should be a hint to you that you need to set up your ice table and solve for X. So they also don't give you the equations for the KSP problems. They expect you to be able to write those, to be able to see that magnesium hydroxide is going to break apart into one magnesium ion and two hydroxide ions. So no ice table stuff here because that's a solid. Here I have 0 plus x. Here I have 0 plus 2x. And I'm going to go through the same process that we just did actually in the previous example, where my KSP is going to be equal to magnesium and hydroxide squared. So let's see, my KSP value is 8.9 times 10 to the negative 12. And then I'm going to have x and 2x squared, so that's going to equal 4x cubed. Same exact process that we just did in the previous problem. I could have just added this on actually, but that's okay. More practice is better. So when I solve for x, that gives me 1.31 times 10 to the negative 4th. This is my molar solubility. That's in units of molarity. That's not my answer. My answer is going to be in grams. So what I need to go ahead and do is remember that if I'm going to solve for grams, then I'm going to need moles. And moles is molarity times liters. So my molarity is what I calculated for molar solubility. It's 1.31 times 10 to the negative 4th. My liters, they gave me 100 milliliters. That's 0.1 liter. Make sure that you are converting that over. Don't plug in milliliters there. And that gives me, I'm going to put it right here, 1.31 times 10 to the negative 5th moles. And I'm still not done because the question is asking me to solve for grams. So I need to convert from 1 mole of magnesium hydroxide, 2 grams. That's why they gave us the molar mass, which was 58.32 grams. Okay, that's going to give me my final answer, which is 7.61 times 10 to the negative 4th grams. So really tiny number there. We're dealing with, remember, magnesium hydroxide is not very soluble. This is telling me how much is going to dissolve in 100 milliliters of that solution. 7.61 times 10 to the negative 4th grams. Let's talk about a couple of factors that can affect solubility. So we're dealing with things that aren't normally very soluble, but there are some things that you can do to increase solubility, or there are some other things that can be done that would actually decrease solubility. So let's look at a couple of those examples. It has to do with Le Chatelier's principle. What you're going to do is you're going to look at the things that are changed in the reaction and figure out if it's going to shift the reaction to the right or to the left. If it shifts the reaction to the left, then it's going to decrease solubility, because it's going to be shifting to the side with more solid. If the change causes the reaction to shift to the right, then it's going to increase the solubility. So adding magnesium ions, that's over here on the left side, the right side, which is going to cause it to shift to the left. And if it shifts to the left, it's going to decrease solubility. Adding hydrogen ions. Couple things that you need to know about this. Hydrogen ions come from acids. So sometimes they'll word the question, what happens if we make the solution more acidic? Also, when we make a solution more acidic, we're lowering the pH value. So you might see it worded this way as well, same type of question. So if we make the solution more acidic and we add hydrogen ions, remember from our Le Chatelier principle lesson that the hydrogen ions are going to react with hydroxide to take it away. And so that's going to cause the reaction to shift to the right and will increase the solubility. Okay, we have another example here. We've got silver chloride. Silver chloride is AgCl, not AgCl2. Let me get rid of that. Just AgCl. So silver chloride has a KSP of 1.5 times 10 to the negative 10. Calculate the molar solubility. So molar solubility is X of silver chloride in a 0.25 molar potassium chloride solution. So here's how this problem is different from the others that we've done so far. We're not going to fill in my ice table right here. In our previous questions, we have just put 0 as our initial concentration for each of these ions. But this is not just dissolved in water. This one is dissolved in a solution that already has chloride ions in it. That chloride concentration is 0.025. So instead of that number being 0, I have a number there instead. And then I have plus X, so 0.025 plus X. And then just regular plus X over here. That's the only difference, is that right there is not 0, because we're not dissolving it in just plain water, we're dissolving it in something that has chloride ions already. But now we just go ahead and solve for X just like how we did before. So if KSP, I'm going to go ahead and write my KSP expression. I don't have any coefficients here, so it's just going to be silver concentration, chloride concentration multiplied together. My KSP value is 1.58 times 10 to the negative 10. And then I have X for silver, and then I have 0.025 plus X. Now, if I keep it like this is going to give me a quadratic equation when I distribute my X through. But remember that when I have a K value that is times 10 to the negative 5th or smaller, I can cross out any X variables that are added or subtracted because it's going to give me such a small number anyways. So then what this becomes is 1.58 times 10 to the negative 10 equals just 0.025X. So from there, much easier to solve for X, which is my molar solubility, which is 6.32 times 10 to the negative 9. Okay, so read the wording of the question carefully. Look for situations where your initial concentrations aren't 0. Look for X's that you can cross out to make the math easy, and you can solve for your molar solubility from there. All right, we've got one last example. Okay, so in this example, we've got 2 different solutions being mixed together. We've got sodium phosphate, we've got barium chloride. So this, again, goes actually a little bit back to unit 3 or 4, whichever one we did solubility in. We have our sodium phosphate, and we're going to mix that with our barium chloride. and it's a double replacement reaction. So when that happens, we're going to end up with NaCl, and so my Na, my Cl here, this is not balanced, and then barium phosphate. And so this particular question is asking if I start with 0.0025 molar concentration of sodium phosphate and 0.0025 molar concentration of barium chloride, am I going to have enough ions there to actually form the precipitate of barium phosphate? Remember, this is going to be soluble. Those are going to be spectator ions. So is the barium phosphate going to precipitate? They give us the KSP value for barium phosphate is 3.4 times 10 to the negative 23rd. Now, this is going to be kind of like our equilibrium questions where we figure out if it's at equilibrium or not. We're going to calculate Q instead of K, and if Q is greater than K, then yes, there's going to be a precipitate, because that means you have enough ions to react. If Q is less than K, then no, there's not going to be a precipitate that's formed. Okay, so here's what I can do. I'm going to go ahead and you can write the overall reaction, which is what I just did. I only did that to show you that barium phosphate was going to be the solid product. That is not required because they actually tell you that it's going to be barium phosphate. What you do need to do is take that precipitate and write the dissociation reaction for that. So that's going to give me 3 barium ions. So we're going to kind of work backwards through this. And then 2 phosphates. And from there, that's going to, if I write my K, remember this is solid over here. If I write my K expression, which is the same as Q, we're going to label that QSP because it's solubility product that we're dealing with here, is going to be my barium concentration cubed and my phosphate ion concentration squared. Now all I have to do is plug in these concentration values. So I'm given concentration values up here. Now you do have to pay attention to, you can't just necessarily plug in those numbers. You have to make sure if the concentration of sodium phosphate is 0.00025, then my sodium concentration would be 3 times that number, but my phosphate concentration is going to be 0.00025. Since there's only one barium in barium chloride, then that concentration is 0.0025 as well. So when I plug in those numbers, my barium concentration is 0.0025. That gets cubed. My phosphate concentration is 0.00025. That gets squared. That's going to give me a Q value of 9.77 times 10 to the negative 16. In that case, now I want to go ahead and take a look at my Q value, take a look at my K, and my Q value is greater than my K value, so yes, a precipitate will form in that reaction. Okay, I don't have that last section of your notes up here on this slide for some reason, but just take a look at that number 2 underneath this example where it says which will precipitate first. Sometimes they'll give you a question with the KSP values and they'll ask you which solid will precipitate first. Always the one with the smallest KSP value, the least soluble substance, will precipitate before something else that's more soluble. All right, and in 714, that we are going to talk about in Unit 9 because it goes along with that discussion of energy that we're going to do in Unit 9. So we are done with Unit 7. I'll see you guys in class. We're going to practice all of these KSP calculations and start getting ready for your test. So I will see you guys in class.